Okay, so backing up, repeat, I am talking about ideas related to application 4 here. You have to go out to StatKey and pick one of their data sets. And you decide on the data set. If you don't know what the numbers mean, the variables mean, then you should ask me. Like if you find the honeybee waggle interesting, but you don't know what they mean by distance and duration, then send me a note and I will send you descriptions of those variables. I've looked up most of these, but not all of them. So pick something there. And then based on, they have the graph for you. You don't need to do anything else. And you can also choose to show the line. And they have the formula for the line, slope, and y-intercept. Based on that, so they do all the work for you, you then have to write up something answering these questions here. So I'm going to do that right now for a different data set. The data set I chose is not in StatKey, but it's some data that I was just thinking about. I'm looking back to the 20th of this month, and I found out how many positive cases are recorded in each Oregon county. And my belief is that the more people there are in a given region packed together, that's population density measured usually in people per square mile, the closer people together there are, the more cases that we'll find. If we're in a more sparsely populated area like Harney and Grant County, where people aren't close together often, we should find less cases. So if you try to look at cases versus population, it's a mess. It looks like a swarm of bees. There's no correlation. But if you take a look at population density versus number of cases, then it turns out there is a correlation. So graphing that data over here, some of these densities are way out there compared to others. So there is a positive trend to this data. I have an R squared here of 0.739. And remember, if you read the book, and if you haven't, please read the book. This is in section 12.3. They talk about R, the correlation coefficient, and R squared, the coefficient of variation. And I'll talk about what each of those means in just a moment. So according to the spreadsheet, in this case, I have a model that says about 3 times x minus 8, roughly, is the model. And I'll write up what x and y are in a second. And then it says R squared is 0.73. So I'm just going to, let's see, I don't think I have those already in here. You do not have to use a spreadsheet. I repeat, you do not have to use a spreadsheet. I could take all of this data and stick it in StatKey. And let's see, do I really want to do that? Nope, StatKey does the same thing. I don't need to put the data in there because that's going to require me to rewrite the data. I'm going to make a calculation here. I'm going to calculate what we call R and R squared to show that they match what the graph shows me. And again, StatKey gives you R right here, correlation 0.86. So that is what I'm calling R here. On a spreadsheet, it's a formula called Pearson. And they want the Y values and the X values. And again, StatKey makes this way easier because they do it for you. Oh shit, wrong button. All right, so I'm getting an R of 0.85-ish. And if I get R squared, that should match the 0.739 given in the graph there. I just take this number above and square it. So if a computer gives you R squared, take the square root to get R. If a computer gives you R, square it to get R squared. So remember, R is the correlation coefficient. And you should read section 12.3 to learn more about it. I'll give you my take on it in just a second. This second number, the square of the correlation coefficient, is called the coefficient of variation. And they tell me two related but different things about the data. The correlation coefficient tells me two things. The correlation coefficient is going to be somewhere between -1 and 1. Negative means it goes downhill, positive means it goes uphill. There's examples of that in the book. This one is positive, which means the data trends uphill, positive slope. So the two things this tells me is that there is a positive slope. Positive slope means that as the, let's see, my x is, I kind of did this backwards. Number of cases, I should have done this the other way, oh well. It means that as the number of cases increases, the population density increases. Increase in one variable causes an increase in the other, and vice versa. Now, that's correlation, not causation. I don't think the number of cases controls the population density. Density increases. And I could also state that the other way, that as the population density increases, the number of cases should increase too. So it could be stated in either direction. Causation is a whole nother thing. I'm just talking about correlation. The other thing that this tells me is since it's close to 1, 0.86-ish is near 1, which is as close as you can get, is perfect correlation. The points perfectly line up. There is strong correlation. And the points aren't that spread out from the line. So just to show some various examples on that, if we look back at the stat key data, this correlation, let's blow that up, 0.864, so the points are relatively close to the line. We got a few that are farther out. If we look at something like the cricket chirps, this one has a correlation of 0.991. That's pretty damn close to 1. Notice how close the points are. If we look at something like, I think the NBA one was pretty spread out. This has a correlation of 0.8. We got a lot more spread on the data. I know there were some that were crazy spread out. Was it the Hollywood movies? Yeah, look at this. Holy shit. Look at the spread there. And the correlation is 0.2, pretty close to 0. So that tells us that, you know, there's not much of a trend to this data. I mean, I can see in the lower bound kind of an uphill trend, but it's pretty damn weak. So is there a relationship between the budget and the audience score? The answer is not much, because that's such a weak correlation there. So correlation tells us two things. If it's positive, it's going uphill. If it's negative, it's going down. Let's see, do we have any negative ones here? Nope. I know there were negative ones somewhere. There we go, negative. So this one shows as the pH increases, the average mercury level decreases. Notice the correlation is a negative number. So 0.5 is like in the middle of weak and strong, and negative just means downhill. All right, back over here. Coefficient of variation tells us something a little bit different. It gives us a percentage of about how variation in one variable affects variation in the other. So are all the number of cases per county the same? The answer is no. There is variation in them. Okay, how much variation? Well, the standard deviation is one measure of how much variation. Are the population densities all the same? The answer is no. There is variation. They're not all the same. Standard deviation gives us a measure of how much variation there is in the population density. The coefficient of variation is related to the standard deviations of each of these lists and how well they line up. So it kind of takes a whole bunch of things and puts them together. This is also in section 12.3, so you should read their description of it. It's similar but different to mine. And so what the coefficient of variation tells us is, let's see, it is 74-ish. So 74% of the variation 74% of the variation in the, whatever my y is here, which is population density, can be explained by the variation in number of cases. So the coefficient of variation, which is the square of the correlation coefficient, is a measure, kind of like standard deviation, is a measure of variation. It's a measure of how much variation in one data set affects variation in the other data set. Now, that's just a mathematical measure. There may be no causation, right? Like the other day I talked about, what was it? The average amount of chicken Americans eat per year versus the amount of precipitation in Montana. And it turns out if there's more precipitation in Montana in a given year, Americans eat more chicken. Right? How does that make any sense, right? That's nonsense. But it has a high coefficient of variation. Okay? Meaning mathematically, we can find a relationship between the two variables, but in reality, there is no relationship between those two variables. Okay? So we have a few different things here. We have a correlation, which just says, do changes in one variable relate to changes in another variable? Okay, that doesn't mean there's a physical reason it happens. Now, in this case, I think there's a physical reason. If you pack a bunch of people close together, you're going to spread that virus, right? So this one has causation, and causation is a reason. But precipitation and eating chicken, don't know about that one. Maybe somebody clever could come up with a relationship between those two, but I don't think so. All right, so can I make predictions with this here? Well, the answer is yes. So if I were to look up number of cases in some region, like maybe we pick on Washington State, pick some county there. List of counties in Washington State. All right, so I go over there and maybe I pick like, what's that, Franklin County. So Franklin County is kind of similar to Umatilla County. It's not very densely populated. If I looked up the number of cases on the 20th and I looked up their population density, then what I should find, if my correlation does truly exist here, and it does, that's pretty high, that their point would fall pretty close to my line here, is what I would find if I plugged it in. So that would be the next thing I do here. I would plug in a number and say, hey, if I found some county had, let's pick on like Umatilla, had 10-ish cases back then, and then I wanted to predict what their population density was, my model does that. And so up here, my model says the slope is 3, the y-intercept is -8. So then if I were to go equals the number of cases times 3 minus 8, then I would expect the population density would be about 22 people per square mile, is what I should find according to the model. If I pick on one of these counties in particular, like let's pick on Tillamook County. Tillamook County says they have 4. So this was just some random unknown county. But if I pick on Tillamook, they had 4 cases back then. And if I use my equation, 3 times the number of cases minus 8, it says their population density should be around 4 people per square mile. In actuality, where'd they go? They were 19. So my model's a little off. Does every point hit this line? The answer is no. So sometimes my model's going to be a little high, sometimes it's going to be a little low, sometimes it's going to be right on. It just kind of depends. But again, these points don't perfectly line up. If they did, R would be 1. So does it make sense for me to interpolate with this model? So interpolate means to pick a number that was within the given range of numbers. So my numbers here ranged from what? What was the high? 3 something? Yeah, from 0 to 320. So to interpolate would mean, in my case, is to pick some number between 0 and 320, because that's the range of my input, and get an output. To extrapolate means to pick something outside of this range. So outside of this range, so again, interpolate, and again, this is in the book too, is within the data set. So that would be picking something between 0 up to 320. And plugging it in and see what I got for output. Does it make sense to interpolate with this? Since it has a strong correlation coefficient, then I should be able to predict, given the square miles of a county, how many cases they should have had on that day. Extrapolate means to go outside of the data set. Extrapolate. And so that would mean picking a number that is greater than 320. Now I can't have less than 0 cases, so I can't extrapolate on the low end, but I could extrapolate on the high end. That should be a 320. So that would mean, say, okay, what if a county had 500 cases on this date? Could I predict their people per square mile? And I would say this is probably a bad idea in this case for a couple of reasons. One, I would want to zoom in on this. This is where most of the Oregon counties fell, and there were a few counties that had a ton of people per square mile. There's a one in the middle here, and there's 3 way out there. And they had pretty varying numbers of cases in terms of their, let's see, what do I have? This is the number of cases down here, and this is the population density up there. So those outliers make me a little nervous about going farther than that because there's not much data in between. So I would say it'd be dangerous to extrapolate. The other thing about extrapolation is just because you have correlation doesn't mean you have causation. But I think there is causation here because if you pack people together, it gives more opportunity for the virus to spread. So I think there is a cause. So it might be safe to extrapolate, but it's a little sketchy given my outliers over there in the data set. And so I would have to do some more research on that. So interpolation, that's usually safe if you have a reasonably high correlation. Extrapolation is only safe if you have a very high correlation and you have a causation, which means you have some kind of scientific reason as to why this number might be big. Okay? And correlation and causation are 2 different things. Okay? Another crazy example of causation and correlation is the number of pirates in the world over the last 100 years has decreased dramatically. On the other hand, the average global temperature has increased. So as pirates drop, temperature rises. So we just need more pirates to bring down the global temperature, right? That's nonsense. So although there might be correlation, a number relating to data sets, there might not be a cause behind it. Different situation. Okay, so that's kind of an overview there, and then you just need to type it up, and when you type it up, make sure you address all of these points here. Make sure you define your variables. What does X mean? What does Y mean? Write that out. So like in my case here, if I were to write that out, and you could write this on paper and take a picture of it, that would work. My pen died, come on pen. About it, there you go. So like for my data, I should probably have switched my variables. I think I would rather have X be population density, population, and you can use different letters than X, but you should say what they mean. Population density of Oregon County. And if that's not clear, be more specific. What's it measured in? People per square mile. So make sure you write up what your variables mean. And then I would like a Y to be number of COVID-19 cases on April 20th was the data set that I picked. All right, that's about all I got for you on that one right there. Again, do not pick a data set. My battery is low, thank you. Do not pick a data set if you don't know what it means. So if there's a data set here you find intriguing and you don't quite get it, then send me a note and I will get back to you about what I believe the variables mean. Otherwise, you won't be able to do things like describe the slope. Oh, let's do that. Slope. So my slope was 3, and I'm going to flip it guys, I want to flip my x and my y. And let's say we're putting this sucker in. Hopefully we'll make it a minute more. So if I choose my variables to be this, then the slope of my model would have been about 1/3, which is about 0.33-ish. And slope for me is rise over run. And my rise here is related to the y, so that would be a change in COVID-19 cases. Because if you're rising, you're changing. And the rise could be a drop, by the way, but we usually use the word rise. And the run means any left or right movement. And so that's related to my population density. So that would be a change in population density. Density. And so to use this fraction over here in words, so I want to combine that with the numbers. And the numbers here, I guess I'm going to go with the decimal version because you're going to get a decimal from StatKey. To write this as a fraction, I would just say, hey, let's just call it 0.33 over 1. And so this would be, let's see, 0.33 over 1 doesn't work so well. Yeah, I guess I'm going to have to rewrite that because I'm talking about number of cases, so I can't have fractions. So let's see, I guess I'm going to go with the 1/3. So this would be 1 more case. And I'm using more because this is a positive number here. Come on, pen. Divided by 1 more. And the population density was people per square mile. So 1 more person per square mile. And I want to put this information in a sentence that my mom would get. So new page here. So what I think the slope means, so slope interpretation, is that for each additional, and usually we start with the independent variable, the x variable, additional, so back here, 1/3 for my slope. So for each additional 3 people per square mile, we expect to find 1 more. Why 1 more? Because that is the numerator. 1 more COVID-19 case. In that county. And again, this is on average, because I'm averaging a ton of different numbers to make this prediction here. So that's what the slope means, and it tends to be more important. So important things about these linear regressions. Back here, the slope is an important number, and the correlation coefficient is an important number. The correlation coefficient just says, hey, is there some mathematical trend to the way these points lay out? And this says, yeah, there's a medium correlation. It's not that strong, it's not that weak, and it's downhill is what the negative tells me. And then the slope tells me how the independent variable affects the dependent variable. And so in my case over here, I'm picking the independent variable to be the people per square mile, and the dependent variable to be the number of COVID cases. And slope is a change. It's a change in one variable affects a change in another. It's not actual amounts, it's changes. Is there an interpretation for the y-intercept? So my y-intercept, let's see, I'm going to recalculate that for this new version. Let's delete that sucker. And I'm going to switch my variables here. So let's insert a row above. This guy is going to be my y, and this guy is going to be my x. And so my slope, just to double check. And again, you do not have to use a spreadsheet here, but it is helpful for the homework. It is y values, comma, x values. And I was guessing at 1/3. It says it's more like 1/4. So that would be about 1/4. And the intercept here, oh shit. Y-intercept, that's the intercept. And I have this in other videos. Now we got a new one here. Y values first, X values second. Oops. In this case, it's +11 when I switch the variables. And remember, so let's see, updating my notes here, correcting. This was about 0.24-ish. And so I'm going to say that's about 1/4. And then the y-intercept is a point, 0 for x, whatever for y. In my case, I just got about 11. So this means, what's my x? 0. So if there are no people per square mile, then there should be 11 cases. What? Does that make any sense? How can you have 11 cases if there's no people? So the y-intercept is just there to kind of balance the slope to fit that. Because if you got rid, like if there's no people, there should be no cases. However, if I graph that, what would happen, and let's graph that, switch the variables, insert column right, move these guys over. All right, so I want to graph these points there. Scatter chart, please. And hey, that looks different. And then throw a line